Over the next set of slides, I will guide you through everything you need to know from Units 1 to 3. We will build up from particle ideas to practical methods in the lab and then zoom in on atomic structure and the periodic table so that when you approach exam questions, you see how these ideas connect. Matter commonly exists in three states: solid, liquid, and gas, and each state is defined by the arrangement and motion of its particles. In a solid, particles are closely packed in an ordered arrangement and they can only vibrate about fixed positions. In a liquid, particles are still close together but are free to slide past one another so that the liquid can flow and take the shape of its container. In a gas, however, the particles are far apart and move randomly at high speeds, so a gas has neither a fixed shape nor a definite volume. The kinetic particle theory explains that all matter is made up of tiny particles that are in constant motion, and that the amount of kinetic energy of those particles determines their speed, and therefore the physical behavior of the substance. As temperature rises, particles gain kinetic energy, move faster, and this causes expansion, increases in pressure for gases, and faster rates of diffusion. When a substance changes state, heat energy is transferred, but the temperature does not change during the actual change of state. On a heating curve, the flat sections correspond to melting or boiling, where the energy is used to break intermolecular forces rather than raise temperature. And this energy that causes a state change without a temperature change is called latent heat. Latent heat of fusion for melting and latent heat of vaporization for boiling. The pressure of a gas arises from many collisions of fast-moving particles with the walls of the container. If the temperature is increased at a constant volume, the particles move faster, so the pressure increases, while if the volume of a gas is decreased at a constant temperature, particles collide more often and therefore pressure increases. These relations are described qualitatively by the gas laws, such as Boyle's law and the direct proportionality between pressure and temperature for fixed volume. Diffusion is the process in which particles spread from a region of higher concentration to a region of lower concentration due to their random movement. Diffusion is fastest in gases because particles are far apart and move more rapidly. It is slower in liquids and negligible in solids, and the rate of diffusion increases with temperature and decreases with greater particle mass, as seen in classic experiments such as ammonia and hydrogen chloride, forming a white ring closer to the HCl end because ammonia diffuses more rapidly. A pure substance has a sharp melting point and a sharp boiling point, while impurities lower and broaden the melting range and usually increase the boiling point. And therefore, one common test of purity is to measure melting or boiling behavior and compare with accepted values for the pure substance. Filtration separates an insoluble solid from a liquid by trapping solid particles on filter paper while the liquid passes through. Crystallization separates a dissolved solid by evaporating the solvent until crystals form and then collecting the solid, and evaporation simply removes the liquid by heating, leaving any dissolved solute as residue. Choose filtration for sand and water, crystallization for obtaining pure salt crystals, and evaporation when the dissolved solid is required rather than the recovery of the solvent. Simple distillation separates a liquid from a solution by boiling the mixture and condensing the vapor to collect a more volatile liquid, while fractional distillation separates liquids with nearer boiling points by using a fractionating column that provides repeated condensation and vaporization steps so that components with slightly different volatilities separate more effectively. Simple distillation is used to obtain pure water from saline water, and fractional distillation is used in refining crude oil or separating ethanol from water. In paper chromatography, a spot of the sample is placed on a baseline and the paper is placed in the solvent so that the solvent rises, carrying components at different rates depending on their solubility and attraction to the paper, and the retention factor, or RF, is defined as the distance traveled by the spot divided by the distance traveled by the solvent front, and can be used to identify substances by comparing with standards under the same conditions. Good practical work requires careful control of variables, repeated measurements for averaging, accurate measurement of volumes and masses using appropriate apparatus, and reporting of uncertainties and anomalous results. When designing an experiment, you should state the independent, dependent, and control variables and how to measure the dependent variable precisely. An atom consists of a central nucleus that contains protons and neutrons and electrons that occupy energy levels or shells around the nucleus. The atomic number, or Z, equals the number of protons and defines the element, while the mass number, or A, is the total number of protons plus neutrons and can be used to calculate the number of neutrons by subtraction. Isotopes are atoms of the same element with the same number of protons but the different number of neutrons or mass number. Isotopes share chemical properties because chemical behavior depends on electrons, but their physical properties such as density and mass differ, and their relative atomic mass is the weighted average of isotope masses using the percentage abundances of each isotope. Electrons occupy shells around the nucleus, and it is sufficient to remember the pattern 288 for shell capacities. The outermost electrons are called valence electrons and control how an element reacts. So, elements in the same group have similar valence electron counts and therefore similar chemical behaviors. Across a period, atomic radius generally decreases because protons increase and pull electrons closer, whereas down an atomic group, atomic radius increases because extra electron shells are added. These size changes explain reactivity trends, such as group 1 metals becoming more reactive down the group because their outer electron is further from the nucleus and therefore easy to remove, and group 17 nonmetals becoming less reactive down the group because it is harder to gain an electron as the outer shell is further away. A strong understanding of particle models, separation techniques, and atomic structures underpins later topics such as bonding, stoichiometry, and reactivity. And in exams, you will frequently be asked to describe, explain, and link these core ideas. Therefore, practice short, descriptive answers, show calculations clearly, and always justify explanations with particle level reasoning. In summary, matter exists as solid, liquid, or gas, and the behavior of these states is explained by particle arrangement and kinetic energy. Separation techniques and purity tests are practical tools to isolate and identify substances and depend on differences in physical properties. Atoms are made of protons, neutrons, and electrons. Isotopes are variants with different neutron counts, and the electron arrangement of an atom explains how it fits into the periodic table and how it will react chemically. When answering exam questions, always begin describe answers with observable facts. Follow explain questions with particle level reasoning, and in calculation questions, show every step with units. Practice interpreting experimental diagrams and lab procedures because practical questions often test experimental design or data interpretation. And finally, time your practice tests to build speed and accuracy. Thank you.